Okay, the probability density is the square of the wave function. It's the probability of finding an electron at a point in space. Most of you are not going to care about these details here. So what is important here? Well, the s orbital is spherical. How do we know it's spherical? Well, the wave function tells us it is. The probability density is going to decrease as you get further and further from the nucleus, just like when we looked at pitching the electron. The probability or the number of electrons that hit outside the circle was less and less as you went further away. We can graph this and look at a plot that looks like a multiple exposure photograph, where you take a picture and that's where the electron is, and then you expose it again a minute later and there's the electron. In that little diagram I made with the orange dots of Andrew, that's sort of like that. It's like, okay, let's take a picture. Where's Andrew? He's here. Wait 2 hours. Where's Andrew? He's here. Wait 2 hours. Oh shoot, he's not even in the picture anymore. It's important to understand that the electron is not moving about the nucleus like a moth around a flame. We tend to think of electrons as particles. It's very understandable. And what would a particle be doing in that region? It would be like zipping around or something, right? But it's a wave. It's occupying the entire space because it's essentially a standing wave. So we can look at pictures like this, and we see this is as a representation of the 1s orbital. It is a fuzzy picture. The 1s orbital is not a ball container that the electron has to be inside of. There's a fuzzy edge. There's not an exact boundary. If we just look at probability density, that wave function squared, we see that the probability is highest at the nucleus and it drops off as you move away. The problem with this is that the one place the electron cannot be is at the nucleus. So we need to do something a little different with our math here. So they use a radial distribution function. So this is the total probability of finding an electron within a thin spherical shell at a distance r from the nucleus. So this is like integrating in calculus, where you're looking at adding up all these little tiny pieces, right? This gives us a better picture of where the electron is found, because now we have two functions that have opposite trends with r. One's getting bigger as r gets bigger, and one's getting smaller as r gets bigger. And the result is we get something like this. So here's the probability as we go distance from the nucleus. So the probability of finding the electron at the nucleus is 0. And that's how it should be. And you go a little bit away and the probability rises steeply. And so this represents where the electron most likely is within this distance from the nucleus. And then as you go further and further out, the probability drops off steeply. Could the electron be out here? Sure. The probability is just very small. And this gives us a maximum at 52.9 picometers from the nucleus, which matches up with the Bohr model, in which the electron has an orbit of 52.9 picometers around the nucleus. But there's a very important conceptual difference. In the Bohr model, the electron is always at 52.9 picometers. It's just going in a nice circle, which is so much easier to think about, right? In the quantum mechanical model, the electron is found at lots of different radii, but the 52.9 is the most likely. Yes?
So the 52.9 is the perimeter of your house, in a sense?
The 52.9, I would say, would be parts of the house, like the kitchen living room area, because there's also this part out here, or perhaps it would be the house itself, and then the yard would be out here, and outside the property, that would be where things are really weird. Yeah. When we go to higher energy levels for the s orbitals, so the second and the third level, those orbitals are also spherical, but now they have nodes in them. So you familiar at all with standing waves on a string? If you get a string vibrating just right here, the string is fixed at both ends, and it's oscillating, and so you can set a wave up that's a standing wave, and so it looks like the string is standing still, and yet it's moving. And there are nodes, and at this node, the string is not moving up and down at all, whereas in the middle, it's moving up and down a great deal. And so this is something like the probability of how far away from the nucleus is the electron. Well, here's a maximum, and then it can't be right there. And then here's another maximum, and it can't be right there. And here's another maximum. It's not even like this, but that's the idea. The electron is a wave. So the orbital is a description of the standing wave that the electron makes around the nucleus. Now, if I want to know exactly where the string is in its movement here, got a high-speed camera and I freeze the frame, I can see the string being right here. But then I can't see the motion anymore. Right? So we have the wave and the particle nature. We could just take a snapshot and see, yeah, it's a particle, it's right there. But then when we're not observing it, it's also a wave, and it's occupying the whole volume. I know. So those distribution functions for the 2s and the 2p, the 2s and the 3s, we get nodes. And so these are like the standing waves on that string, except that they're not nice and symmetrical anymore. But we've got these nodes. So every principal energy level has one s orbital. Every floor on the hotel has one s room. The s room has one bed in it. It can hold 2 electrons. That's always the lowest energy orbital in that level. So on a given floor in the hotel, the s room is the cheapest. Maybe because it's closest to the elevators and the ice machines, and it's not as quiet as the ones further down the hall. I don't know. The p orbitals are present on the 2nd floor, 3rd floor, etc. of the hotel. Principal energy levels above n equals 1. And here we're going to have 3 p orbitals, and they're going to be oriented differently in space so that they're not on top of each other. These are 2-lobed. They kind of look like dumbbells or balloons. So here's, like 2 balloons, but there's this gap in the middle. And so this is one orbital. This is one wave for the electron, and this actually looks the most like a standing wave on a string. Right? So it can't be in the middle, and here's the most probable, and here's the most probable. The electron is on both sides of the nucleus at the same time because it's a wave. I know. So there's one orbital along the x-axis, there's one orbital along the y-axis, and one along the z-axis. They're perpendicular to each other. Now, what's the exact orientation of the x-axis? I don't know. It's relative to the other orbitals. Then there's the d orbitals. Yeah, there's details. This is what they look like. The first 4 aren't so bad. They kind of look like doubled p orbitals, right? So here we've got 4 lobes instead of 2. And there's one in the YZ plane, and one in the XY plane, and one in the XZ plane. And this one is in the x squared, y squared plane. And then there's this guy. Where did these shapes come from? These shapes came from solutions to Schrodinger's equation using the 4 different quantum numbers. So we didn't just make these things up. I mean, who would do that? And then the f orbitals.
Are the values of m sub l assigned specifically to each of these orbitals?
That's a good question. I think that they are. For the p orbitals, since they all have the same shape, it probably just doesn't really matter. But when you get to the d and especially the f, now we have different shapes. And so then it would matter. Off the top of my head, I don't know which is which, and I don't care, honestly.
So for the D and the F, like, is it always meaning equals to how it is?
Yeah, so if n equals 1, you can only have s orbitals. For n equals 2, you've got s and p. For n equals 3, s, p, and d. And you don't get the f's until you get up to the 4th level. And so the possibility of g's wouldn't happen until the 5th level, right? Orbitals are determined from mathematical wave functions, and waves have phases. The wave function can be positive or negative. At the node, the wave function is 0. And the sign of the wave function is called the phase. And when the orbitals interact, their wave functions can interact in phase, having the same sign, constructive interference, or out of phase, opposite signs, destructive interference, as waves can interfere with each other. And we'll learn more about this when we talk about valence bond theory. But here's the idea. It's a little hard to understand how the s orbital could have a phase because it's just this one thing. The p orbital is easier because we see that one lobe is positive and one is negative phase. But the s orbital can be positive or negative, and so then they can interact with each other. So that's like foreshadowing for a future chapter. We talk about atoms as being spherical, and they are, because when you put all of those orbitals together and superimpose them, the shape is roughly spherical. If you just looked at the s and the p, you'd have these like bumps sticking out. But then you've got the d's and the f's, and those fill in those gaps, and so overall the atom is roughly spherical.